Welcome everybody. My name is Hannes Engler, researcher at the Institute of Grapevine Breeding of the JKI in Siebelingen, Germany. Today I will talk about the use of artificial intelligence for grapevine yield forecast and breeding research. First, I want to give you a short overview of the importance of yield in viticulture. Especially in viticulture, yield is linked closely to the quality of the grapes. These two parameters determine economic viability. A higher yield leads to a lower wine quality. Until today, yield estimation is usually done manually. For this, the winemaker counts the number of bunches per vine of at least 40 vines per field and divides it through the standing space of the vine, which is calculated from the distance between the rows and the distance between the vines in the row. This gives him the number of bunches per square meter. If he multiplies this with the average bunch weight of the respective variety, he gets the yield per square meter, which can be extrapolated to the total field size. This method is very time-consuming, especially considering the small field sizes in viticulture and the high number of individual fields. Furthermore, this results in high error rates of up to 30%. The manual yield estimation shows also a variability within and between the individual fields. Errors under 10 or under 5% are required by the wine industry to ensure planning reliability. And also for breeding research, yield is still an important breeding trait. Yield of wines is composed of various compounds. These are the number of shoots, the number of bunches per shoot, berries per bunch, and the berry weight. Yield is also influenced by a number of biotic and abiotic factors like the climatic conditions, the nutrient supply, management practice, disease pressure, and also extreme weather conditions. In our project KI Repro, we see the aims in two different areas. First, the winemaking. Here, accurate yield estimation can improve the quality management and the harvest and winery logistics, whereby costs can be reduced. For this, the consideration on the plot level is crucial. Secondly, the breeding research. Here, we can use the artificial intelligence for phenotyping and the screening of breeding material. For this, the consideration on a single wine level is important, because of some genotypes there are only single wines in the field. As the first step in the project, we developed a yield forecast model. For this, we use long-term yield data from a local cooperative, long-term weather data from around 20 weather stations around the area. The allocation of individual plots to a weather station was done by the distance to the next weather station. Also, we use soil parameters and process management data. For the development, we split the yield data of one variety into training and test datasets. The training data are used for the machine learning process and the test data for the validation and to determine the prediction error. In this process, we had to deal with inconsistencies. The yield data are not recorded precisely enough in the last 16 years for individual plots. For example, we found for the variety Dornfelder in several years in the plots of different winemakers unrealistically high yields per area of up to 700,000 kilograms per hectare. The average yield in Germany for Dornfelder is around 17,000 kilograms per hectare. This is a result of the problem that winemakers book the yield of several fields on only one field in the cooperative. Another problem was that the weather data are not available from all weather stations throughout the entire period. Most data is available from 2008 on. Also, process management data is only available from some certain plots. These inconsistencies can weaken the whole estimation, because we only have a relatively small number of fields at our disposal for the machine learning process. Therefore, the historical data must be screened very carefully before they can be used. This is an important first conclusion of the project and shows the importance of digitalization for research data management. So far, the artificial intelligence can forecast yield with an error of 20.3% correctly, just by using the inconsistent historic data. Now I want to give you a short outlook about the next steps in the project. To further minimize the prediction error, the artificial intelligence will be extended and further improved by sensor-based feature acquisition. For this, we use the PhenoBox, which is an embedded vision system that was placed last season in the front of the Phenoliner, a converted grapevine harvester as phenotyping platform. With the PhenoBox, we will record yield-relevant characteristics like the number of shoots, the number of bunches, or also the dormant pruning wood directly in the field in real time at different stages of development in the vegetation period. In the long run, the sensor data acquisition needs to be carried out casually doing standard vineyard work on the tractor. To get closer to this goal, we will mount the PhenoBox on an all-terrain vehicle in the coming season. We are also recording the nutrient and chlorophyll content in the leaves, as well as soil samples to be able to make a conclusion about the vitality of the vines. The feature acquisition is also the main part for phenotyping and the screening of breeding material. At the end of my presentation, I want to thank Madeleine Stoll as the technical assistant in the project, all project partners, and the Federal Ministry. And I want to thank you for your attention.